Hello everyone, welcome back to the course on measurement and instrumentation, and today is the third lecture of 12th week. This is the last week of this course and we are discussing data acquisition system. Today we are going to discuss about process control. Although process control is a typical part of a course control systems, as well as we have courses on advanced control systems, but if you have not taken the courses on control systems or advanced control system, this will give you an overview that why controllers are required and what kind of controllers are available. Although we will not go in depth, but as I have mentioned that there is a whole dedicated course dedicated to only control systems, but what I will try to do is I will just try to give you an overview so that you can understand that how a control system is an important and integral part of any measurement and instrumentation, particularly the data acquisition system. Okay. So when I say process control, it is used to maintain a process variable, for example, a temperature, pressure, flow or level at desired value, which is known as a set point. So for example, if you are sitting in a room, you have set the air conditioner at a temperature say 10 degrees Celsius or say 20 degrees Celsius, whatever. Okay. Now you want the room to be at 20 degrees Celsius only and you do not want any kind of deviation from that. Okay. So that is your set point, and your process, say in this case small AC, is trying to maintain that 20 degrees Celsius for whatever time you power it up. Okay. So a process control is used to maintain a process variable, for example all this temperature, pressure and all, okay, at a desired value which is known as a set point. Okay. A process control system maintains a process variable at a desired value. For that it uses a kind of feedback control system or feedback system. So this is a typical process control system. You can see that I have a controller, actuator, plant and a feedback where a sensor is connected. Okay. So a basic control system consists of all these parameters that you are seeing. You have sensors, actuators, plants, control system and all. Okay. The sensor measures the process variable and convert it into an electrical signal, okay, which you can see over here, and this is fed to a controller. The controller compares the set point with the measured value and determine the corrective action. When I say corrective action, means that it generates a kind of error signal. So error in this case is a set point minus the process variable PV. So SP minus PB. You wanted it to be 0, but any deviation from set point in the process variable is actually the error which is given by your controller. Okay. Now the actuator, which is the next subsequent stage, converts the controller output into a physical action. For example, you want control valve to open or close, you want the motor to be switch on or switch off. Similarly, you want your heater to be particular temperature and so on. Okay. Now everything whatever you are doing is to control a process or a plant. Okay. So the process is the actual system or equipment that is being controlled by all this control system. Okay. Now example of processes can be several, like I have just given you an example of a room heater or say a room cooler or room AC. Okay. Similarly, you can say that a boiling temperature control system, water level in a tank, chemical reaction in a chemical reactor temperature, conveyor belt speed control, and it can be even more complex depending on where you are utilizing them. Okay. Now for all these you need control loops. Okay. They form the core of the control system basically, and continuously monitoring and adjusting process variable like flow or temperature to match the set point is only possible because of these control loops. Okay. They integrate sensor, controller and actuator in a feedback cycle. Okay. There are 3 different type of process loops present in any process control. Like I have open loop control. There are instances where you use a feed forward control system, and with another process loop which is known as feedback or closed loop control, which is the most prominent and most useful form of any process loop. Okay. When I say open loop control, this is a typical example of open loop control. Okay. A typical open loop control path diagram is shown over here. Here R is the set point, D is the load disturbance, and E is the error voltage generated from this set point, deviation from this set point in this load disturbance. Okay. You have subsequent stages like signal conditioning, actuator, and the process where you have D1 as a process disturbance. Okay. Here R and D are unmeasured variables. So if you have R and D as an unmeasured variable, it definitely means that this E is also an unmeasured variable. Okay. Therefore, if there is process disturbance D1, it is difficult for error voltage E to control the process. Okay. And therefore, open loop control is usually not desired. Okay. And we have other alternatives like feed forward control. Okay. This is a typical example of feed forward control. Okay. Feed forward control operate as an open loop system, as you have seen just now. Okay. It does not depend on the output error signal, and it uses a measured disturbance signal EM. EU is, you can understand, a intermediate error signal that is generated, okay, and detects changes in load or disturbance before they affect the actual system. Okay. Now this feed forward control system provides any anticipatory actions and take corrective action in advance to reduce the disturbance impact. Okay. It works alongside the feedback control. So you will see that you have always feedback control and then you have feed forward control system. Okay. So feed forward systems handles known disturbances where the disturbances are already measured, while feedback corrects any other remaining errors. Okay. So it improves overall system performance and minimizes the effect of both measured and unmeasured disturbances, particularly when you use it in conjugation with the feedback control system. So let us see feedback control system, which is very essential part of any process control. Okay. The block diagram of a feedback control loop is shown over here. Okay. You have this signal processing unit, actuator, final control element, the process which is getting disturbed by say signal D1, and then you have measurement, and then we have a feedback gain. Okay. Now in feedback loop, the set point is compared to the feedback of measured value of process variable, and control action is taken by error signal EM through the actuation of the final control element. Okay. The measured variable is monitored continuously for modern automated controller. The load distribution is measured in the feedback controller, and control action is instantaneous with little delay for any disturbance in the process. The disturbance is created in the form of D1 that you have seen. Okay. Now this is the control loop, but one thing that is inherent to any kind of control system or any control loop that you have just seen is the controller. Okay. Controller plays very important role because it actually gives you the opportunity to compare the set point with the feedback element, whatever you are feeding it back. Okay. There are different type of controllers available in the modern measurement and instrumentation. Okay. We have on-off controller, which is the kind of simplest controller available. Then we have a proportional controller, sometimes only denoted as P controller. Okay. We have proportional integral controller, PI controller. We have a proportional derivative or PD controllers. We also have a proportional integral derivative PID controller, which is very popular. Okay. Then we have a programmable logic controller, PLC. This PLC is a kind of digital controller. We will see this in detail. Okay. But before we proceed to PLC, let us see all these kind of controllers in brief. Okay. Let us start with our on-off controller. The on-off controller is the simplest form of automatic control. Controller output, as the name suggests, is either fully on or fully off. You cannot have an intermediate stage. Okay. When process value falls below a certain set point, the controller turns on, while when process value exceeds the set point, the controller turns off. Okay. This is also depicted in the transfer curve for on-off controller, where set point is shown over here. Okay. The figure suggests that corrective action is taken by the controller only when manipulated or error is non-zero. Okay. Now the gain of this type of controller is infinity for ideal case, while it is actually not infinity in practical case, and it is very high, like of the order of thousands, okay, for practical cases. Okay. The process reaction curve of on-off controller is shown over here. This is the actual process reaction curve. Okay. Now if you see, I have dead zone over here. I have a dead zone integrated in this process control curve. Okay. For ideal on-off controller, the dead zone will be 0, while in practical case the dead zone is about 1% of the set point. Now this is the basic controller, and in some advanced controllers I have a proportional controller or P controller. A proportional controller provides energy input proportional to the manipulated variable, so that the process to an extent is balanced in the energy demand. Okay. As the name suggests, the proportional controller provide energy input proportional to the manipulated variable. Okay. The transfer curve of a proportional controller is shown over here. In this case, this LSP is the lower set point, while this USP is the upper set point, and set point is somewhere here. Okay. Now this proportional controller has faster response as compared to a on-off control, and they reduces oscillation that you have seen in case of a practical on-off controllers. Okay. However, they produces steady state error, or sometimes known as offset error, which can be further taken care. Okay. Then we have proportional derivative or PD controllers. So derivation of a quickly varying error signal generates a varying signal which leads the error signal in time, and therefore derivative action is an anticipatory action. Okay. So a schematic of a proportional derivative controller or PD controller is shown over here. You can see that along with the proportional circuit, I have a derivative action in place. Okay. The derivative action has the ability to shift proportional band up and down for a quickly varying process variable. The amount of shift of the proportional band is proportional to the rate at which the error signal is varying. Therefore, it is also known as rate action controller. As the derivative action works in a way to collaborate with the rapidly changing process variable, it is used to compensate the startup overshoot of the PI controller and also act properly in case of step change in the set points. Therefore, they also being used in conjugation with the PI controllers. Okay. The PI controller combines proportional action with integral action, as you can see in this schematic. Okay. The proportional action reacts to the present error, as you have also seen in the proportional derivative controller. However, we have seen that the derivative action was kind of anticipatory action. However, the integral action removes any accumulated error. Okay. So this is in brief about all these PI and PD controllers, and combining them we have a PID controller or proportional integral derivative control system. Okay, which is even more popular than whatever we have seen. Okay. A PID controller combines all these three control actions, and we have seen from our previous slides that proportional actually reacts to the present error because it is directly proportional to whatever signal or error signal you are feeding. Okay. The integral removes any steady state error, while the derivative predicts the future error, as we have seen that it is kind of anticipatory action taken by the derivatives. Okay. So in the PID, the proportional part is for to react to the present error. Integral removes any steady state error, while the derivative predicts any future error, and by this you can have even better control whatever we have seen over that. Okay. So the PID controllers has several advantages, like it has a high accuracy, they have fast response and widely used in the industrial automation. Okay. Then comes the digital controllers, which is very essential nowadays, all kind of automation systems, okay, which is known as programmable logic controllers or PLC. Okay, or we can also call it programmable controllers. Okay. The PI, PD and PID controllers that we have just seen can be physically implemented using all kind of electronic circuits, mostly based on op-amps and other passive elements like resistor, capacitors and so on, in conjugation with this operational amplifier. Okay. In modern industrial system, controllers are field programmable controllers, commonly known as programmable logic controllers, PLCs. Okay. These controllers, as I have mentioned, are digital controllers and are microprocessor based programmable devices used for industrial control. Programmable controllers or programmable logic controllers allows several control parameter settings, including the set point, where we have also seen in case of other controllers where we want desired value of the process variable. It can also set you upper set point or USP or lower set point, which are the upper limit of the control range and lower limit of the control range. Okay, so I mean, these are just some example. It can help you to set enormous amount of things in a control system. I mean, it gives you a better opportunity to have better control over all the process parameters. Okay, PLC can be configured to accept signals from multiple input channels, typically 4 to 16 inputs. Modern industrial control systems are heavily dependent on these PLCs. Okay, they provide flexible programming, multiple input-output configuration, and easy implementation of P, PI, and PID control actions in digital way. Okay, PLC is a processor-oriented digital device used to perform logical operation in discrete industrial control system. In a discrete logic system, operations occur sequentially, where input are switching devices and output are relays and coils. The older generation controllers, I would say, not logic controllers, were heavily dependent on relays. So input also you had relays and output also you had relays. So it has totally obsolete that kind of configuration. Okay, earlier industries used mechanical relays and connectors and contactors for sequential control, but these became obsolete due to mechanical failures. And also in practical sense, if you see, even for a small changes, I cannot change all the relays configuration, or I cannot do rewiring for where thousands of relays are working together. Okay, so a simple program has taken over that. Okay, mechanical relay systems also require large energy for operation and produce high mechanical noise due to chattering. It also requires a lot of space to accommodate all these relays. Okay, with the development of power electronic devices, for example SCR, TRIAC, DIAC, IGBT and MOSFETs, mechanical relays and contactors were replaced by all these solid state devices. PLC allows easy implementation and modification of control logic using user-friendly diagrams and provides proper isolation using optocouplers between processor circuits and power devices. Modern PLCs can communicate data between multiple PLCs. It can also communicate data between a computer and a PLC, or even between a distributed control system DCS and a PLC. They are widely used in industrial application, for example in the material handling system, in the weaving mills, food processing industries, machine handling systems, robotics, and can also work as a local control in the DCS, distributed control systems. Okay. A discrete state means a particular condition of the system defined by the status of different devices. These conditions can be expressed by statements. For example, you can say that certain valve, say A, is open, a valve for example say B is closed, a conveyor say C is on, and so on. I mean you can give these conditions as these sentences. Okay. At any moment, the state of the process is determined by the combination of all input and output conditions. Since each variable usually has two states, either on or off, the system can have a limited number of possible states. Say if there are 3 input variables and 3 output variables, the state is defined by total 6 variables, and the total number of possible states will be 2 to the power 6 or 64. So 64 total number of possible states can be there when you have 3 input variable and 3 output variable. Okay. An event in the system represent a particular state, a specific assignment of output value for given input value. So you have number of choices, okay, and you can generate as many sentences as you can do. Okay. The event continues as long as input variables and output variables remain in the same state. For example, say event 1 can be a temperature is low, heater should be off. Event 2 can be temperature is low, light has to be on. Event 3 can be temperature is high, light has to be off. Similarly, event 4 can be temperature is high, heater is on, and so on. I mean, you can have n number of and in this case say 64 number of events sequentially, and you can have that many parameter to be controlled. Okay. An event occurs when the system moves from one state to another, and such discrete state or sequential event processes are controlled using a PLC. Okay. So there are different characteristic functions of PLC. Let's see some of them. like they are field programmable. Okay. PLC can be programmed and modified by the user directly in the field without rewiring or sending the unit back to the manufacturer. It is a completely a user defined programs can be written to it directly in the field. Okay. Please note that these things were not possible with the mechanical relays. So if you want to have any kind of changes, user defined changes, you have to rely upon the manufacturer. Either you may have to call them or you may have to send the complete relay system to them for any change in the wiring configuration. Okay. So similarly, they have programmable functions. So PLC perform functions, for example, logic control, timing, counting and memory operations through control oriented programming languages. We will see some of them. Okay. They have deterministic scanning. So PLC scans its memory and input output in a fixed sequence called the scan cycle, and this ensures the machine or process respond predictably according to the program that is already written in the system. Okay. They have diagnostic capability. Okay. PLC performs error checking and internal test of memory, processor and input output system can be done using this PLC. We will see a flow diagram of a PLC, that how it operates and how it reaches to this error. You can say that how they take this error commands. Okay. They have monitoring capability. PLC can monitor system operations using indicator lights or external displays. Okay. These are flexible control devices. So PLC is not designed for only one application. It can handle a wide variety of industrial control tasks depending on what user require. Okay. PLC is a compact and appropriately packaged device for industrial environment. So you can say that they have a proper packaging to be deployed in all kind of harsh environment. Okay. A typical block diagram of PLC looks something like this. You have an input module, you have an output module, and in between you have a processor which has different units, and this communicate using a ladder program. Okay. Let's see them one by one. Let's see first the input module where your input is provided to this. So this input module receives signal from field devices. For example, it can be a simple push button or it can be limited switches, proximity switches. It can be input can be from different sensors like temperature sensor, pressure sensor or so on. So the input module, it is at the forefront and its work is to receive signal from any field device. Okay. Then we have a logic solver which is also called the processor of this PLC. Okay. These PLC or this processor actually is the place where control programs are executed and any logical operations are performed. Okay. Usually they are normally open NO or they can be normally closed depending on the program written into it. When I say normally open or NO contact, so NO means the contact is open in the normal state, means that there is no current is flowing. Okay. When the switch or input is activated, the contact closes and current flows. A push button that only allows current when pressed. Okay. Then we have NC or normally closed contact. Normally closed means the contact is closed in the normal state, means that current flows. When the switch or input is activated, the contact opens and current stops. Then we have memory interaction. The processor interacts with the RAM or ROM of this device where the ladder program and operational data are stored. Then we have a programmable ladder or monitor. The control program is written in the ladder diagram form and downloaded to the PLC memory for execution. Then we have output module. Now this program, this output module, the work of this output module is to send control signals to actuators, which is the subsequent stage that we have seen in the first slide where I have mentioned that we have a controller where this error signal is compared with the set point and followed with we have a actuator. So this output module works like this. It has to send control signals to actuators depending on what this processor has fed into it, and the output devices such as solenoids, relays, contactors, motor coils, valves are directly connected with this output module as they are the actuator which is being controlled by this PLC. Okay. Now let us see working of this PLC. And we have already seen all these components, so it will be very easy for us to understand their operation. The PLC reads the input signal, processes them according to the stored program, and then updates the output devices. Okay. The processor section is the main part of a PLC. This controls and coordinates all system operation of the PLC. It processes input signal using the stored program and generates the required output signal through the power supply, memory, CPU, and the input-output interfaces. So I can say that the processor section has this 4 important constituent. I have a power supply, a memory, then central processing unit CPU, and then I have a input-output interfaces. The power supply section of this processor provides regular DC voltage to the PLC, and common supply level for this kind of devices are DC level of the order of 5 to 12 volt. This ensures stable operation of the processor and as well as the memory circuits. Then we have memory section. PLC memory section stores the control program as well as the system data, and there are different type of memory systems that exist. We have CMOS RAM, which has already a battery backup, which stores the user program, and the battery backup prevents data loss during any kind of power failure. Then we have non-volatile memories also in the form of EPROM as well as EPP-ROM. So EPROM, which is the electrically programmable ROM, is again a type of non-volatile memory, and program remains stored even without any kind of power. Then we have EEP-ROM, which is the electrically erasable programmable ROM. This can be erased and reprogrammed electrically, and these are used for long-term program storage in PLC. Then we have a CPU in this processor, which is as the name suggests, central processing unit is the main processing unit of the PLC, which controls all operations going on. Okay. The flexibility of the PLC depends on the design of the CPU, including the possibility of any kind of future expansion in this PLC. Okay. The CPU speed determines how fast the PLC scan the memory and execute any program. This speed is called the scan rate, usually expressed in millisecond per 1000 words of the scanned memory. PLC scan rate is often specified using contacts and coil operation. Programs that use timers, counters, and mathematical functions may require more execution time. Now let us see basic flow chart, which represents the basic operating cycle of a PLC process software. Okay. Because process software is what is controlling everything in this PLC. Okay. Now you can see this chart, okay, flow chart. The first stage is power up, then we have program diagnostic check. We'll see that if there is a fault, what will happen, and if there is no fault, there is a scan input, then solve logic, scan output, communication, then perform diagnostic check, then if there is fault, what has to be done, and then if there is no fault, this cycle repeats. Okay. Now this flow chart represents the basic operating cycle of a PLC processor software, showing how inputs are scanned, how logic is executed, and how outputs are updated. Let's see these steps in very brief. Okay. The first stage is the power up. Okay. When the PLC is switched on, the system starts the initialization process. Okay. Then we have program diagnostic check. The PLC check the program and internal hardwares to detect any error. If a fault is detected, the PLC moves to the fault handling stage, and then it actually comes here and this sequence will be executed. We'll come back to this. Okay. Then if it is not there, if there is no fault, we have scan input. The PLC reads the status of all input devices, whatever is connected to it, be it sensors, switches, or any kind of push buttons. Okay. Then it reaches to solve logic stage, where the CPU processes the control program written in the logic, ladder program. So ladder logic it reads using the input data. Okay. Then it scan the output, then there is a communication, then it has the perform diagnostic check. The PLC continuously check the system for any error or fault during this operation, and if there is a fault condition, the PLC sets the output to a safe state and wait until the fault is cleared. Okay. In case of power failure, means that if this stage is itself not executed and if there is a power fail, it goes into this sequence, okay, and the PLC turns output off and prepare for the next power up. Okay. Then if no faults occur, like if it is only here, the PLC repeats the scan continuously. Okay. So, you have input scan to all this logic execution to the output scan. Now, we have understood even the process software condition. Please note that I have replaced all the relays that was present in the older generation control systems using this program. Now, everything is now controlled by a simple computer. So, you can understand that this programmable logic controller PLC as a mini computer as well. Okay. Now, PLC can execute multiple tasks within a single process. Some PLC support sequential functional chart SFC for limited multitasking. However, multitasking is always possible. Okay. Multitasking mainly occurs in two forms in PLC. One is the time driven multitasking and we have also a event driven multitasking. Okay. Let's understand what I mean by time driven multitasking. Here the tasks are executed at specific periodic time intervals. Okay. The user assigns separate input output operation for each task. Important tasks, say for example high speed motion control or a fault detection which has to be done immediately, runs more frequently, and less critical tasks like indicator lights or display functions run more slowly on the system. Okay. Then we have event driven multitasking, which is even kind of more powerful multitasking. Here this is also known as interrupt driven multitasking. A task is executed when specific event occurs. For example, pressing a push button triggers particular task. Okay. So, it will not depend on the time, but it will depend on what user want. So, it is a kind of task dependent event. Okay. Then let's also quickly try to understand the user software in this PLCs, because we are mentioning continuously that it gives you more control as compared to the conventional controllers. Okay. So, the user software in any PLC is written by the control engineers and stored in a PLC memory. This is used to control and monitor the machines or processes that is connected directly with this PLC. So, this contains configuration data or the system environment information, as well as it also contains the language program, which is the control logic. Okay. So, when I say configuration data, it defines the hardware setup and operating environment of the PLC system, and it includes details, for example, input output assignment, memory allocation and communication settings. Then we have language program, which is more controlled by the users, contains the control logic written by the engineer to control the machine or process and determine how inputs are processed and outputs are generated in the PLC. Okay. There are different type of language software that a PLC uses, like we have state languages, Boolean languages, high level languages and ladder languages, this being the most frequently used, although Boolean language is also sometimes preferred. Okay. So, Boolean language is commonly used in PLC programming. It uses logical instruction, for example and, or, not and recall to store to describe the program logics. Okay. It is mainly used to represent logic operations in control programs, and debugging is not easy unless single stepping feature is used. Single stepping slows down the program execution, but helps observe the effect of input output clearly, and that is why there are different other programs, like as I have mentioned the ladder diagram, which is more PLCs prefer ladder diagram over any Boolean language as well. Okay. PLCs generally uses ladder diagrams to represent logics or sequences of events. This ladder programming explains the system states which are closer to the field instrumentation, and it is easier to understand compared to Boolean language programming. That is why I mentioned that this ladder diagram are more frequently used in PLC as compared to the Boolean programming. ladder diagrams uses field instrumentation objects to represent control operations. Okay. Now there are enormous amount of advantages provided by this ladder language, and that's why they are more preferred in PLCs. It is readily understood and maintained by any skilled worker. It provides graphical display or program execution by sharing power flow through the ladder design. Okay, and the program is also fast. It generates more readable program for sequential control. Okay. Now this PLC, their application is tremendous. In all kind of modern control systems, these PLCs are deployed, and the conventional relay based systems has completely been obsolete, be it in industrial automation, for any kind of process control, even in the measurement and instrumentation, particularly in the data acquisition, these PLCs are used. For the manufacturing and assembly lines, they are preferred. For power plant control system, for water and wastewater treatment plants, everywhere you will find that PLCs has taken over the conventional relay based system. So with this, I hope that the idea of process control is clear to you, that why process control is used in any measurement and instrumentation, and how the processes, particularly the process of measurement or setting up a particular temperature, pressure and all, is controlled by the system. Thank you.